All right, so it's a pleasure to have Angshuman Choudhury, who'll tell us about low temperature energy dynamics of SYK models.
Yes. Hello everyone. Thank you to the organizers for letting me discuss about my topic. So yes, I'll be talking about low temperature energy dynamics of SYK models. So firstly, what is the SYK model and why is it interesting? So the SYK model is a 0+1 dimensional system of n Majorana fermions, which are randomly interacting 4 at a time. And you can see that from the image at the bottom right. And the coupling between these fermions is a Gaussian random variable with 0 mean and non-zero variance. And you can see that from the Hamiltonian expression over there, where this J has 0 mean and a non-zero variance. Why is it interesting? Well, when we put these, or what we call as SYK dots, and we put them into a lattice and we have some small hopping perturbation, or in fact, even if we couple them with an SYK-like coupling, these have a linear anti-resistivity, which is shown, and the large N limit is technically done so that it is analytically solvable. And yes, the second more important thing also is that there's this holographic duality that exists, which was shown by Kitaev. And yeah, it has the same effective action as a theory of gravity in nearly ADS2 spacetime. And the aim here is to find the low energy dynamics as a toy model for strange metallic behavior. However, the problem is that the SYK model itself is, as I said, quite difficult to solve analytically. And we then do a small modification, which is that instead of allowing 4 to interact at a time, we generalize it and make it Q at a time. And in the limit where N is much larger than Q squared, much larger than 1, this model becomes analytically tractable. And the advantage also is that, and why this also is allowed is because the effective action has been shown to be qualitatively the same. Obviously, the quantities themselves will change slightly, but at least the qualitative physics still remains the same. And what we do to allow stuff like transport to occur is that we place each of these SYQ dots into a lattice chain, and the lattice itself has periodic boundary conditions, and we allow for nearest neighbor SYK-like interaction. To this end, this is sort of a diagram. So obviously you have the Hamiltonian there, but you can easily understand it with the diagram. So you have these, so I've set Q equals Fourier for simplicity. So you have these interactions within each dot, which is SYK-like, but we also allow Q/2, Q/2 body interactions between nearest neighbors. And yeah, so from the Hamiltonian, also you can see that, and yeah, it is the same sort of generalization of the model. Yes?
Just to be clear, in your model, the coupling between the dots is always SYK4, even as you crank up Q.
No, it's SYK-Q. It is,
so
it's
both
Q
the
by
coupling
2.
and inside.
Yeah, yeah.
So can I also ask a question? Maybe this is too naive, but if you have like that many fermions, wouldn't such an interaction be irrelevant? At least like into 4. Does this not matter? Like if you couple all the fermions together from an RG sense?
Yes, I think you can. Yeah, I don't think it is a
It's not an issue?
I don't think so. Okay. So then there's a lot of calculation that occurs, but what you can do is, well, you can find the retarded energy density 2-point function, which is given at the top. Now, of course, there's a lot of different variables that are dependent upon each other, which are well defined. But the important things to look over there, which are defined, is this H, which we'll look at later, which has this gamma quantity, which basically tells us how strong the interaction is between different neighbor lattice sites as compared to its self-interaction. When gamma is 1, it means that the self-interaction is negligible compared to interactions between nearest neighbors, while if it's 0, it means the opposite. And that is one important quantity. And the other important quantity to look at is the momentum itself is all encoded in this variable h. This h has a significance, which we'll see later. But as a teaser, it is basically going to be it's going to be the dimension of the energy density coupling itself. So like when we look at it in the CFT sense, from a CFT, the dimension of the energy is going to be h exactly. Yes.
Why does this correlation function only depend on frequency? I mean, you put space into the problem, right? You have these coupled.
Yes, I mean, technically, yes, it should be omega comma p, and the p is determined via h. So h has momentum in it. Yeah, so it should be omega comma p, yes.
I see.
Yeah.
So when you say diffusive, I mean, you really mean diffusive in the ordinary sense. Okay,
Yes,
there
yes,
is
yes. Yeah, so let's look into that in more detail. But the idea is that we're going to be looking at the poles of this function. And as you were saying about diffusive, so what we were expecting with the pole structure is that we have we have energy conservation because the Hamiltonian does not have any time dependence. And due to this, from Fourier's law and from definition of specific heat, we can substitute these into the energy conservation law and then Fourier transform it. And from there, get exactly the diffusion equation to have that diffusive behavior which you're talking about. And so we should expect a diffusive pole to occur in our Green's function. So that is one thing that we expect. The second thing that we expect, as from the talks from yesterday, was that since we have CFT that is occurring as an artifact of our calculations in the IR, we have this short chain action that appears, and this has a SL2R symmetry. And from there, you can find the Green's function directly. And we get something like that occurs from the CFT data. And as I was saying, this delta of K is the dimension of the operator. And since we're looking at energy, it's going to be h of K. But I've just written this again for simplicity. Yes?
So this SL2R is for a single SYK dot, right? Or it's for the entire chain?
It is for the single dot and the SYK chain in our case because they're the same sort of terms. Like in the SYK dot also you have SL2R. If we look at the chain and then since the interaction terms are the same form, they're both Q-like interaction terms, it will simply just redefine the way like this the coupling constants will add up quadratically in our calculations.
But this SL2R is kind of like the 0 plus 1D CFT like thing.
Yes.
This is d-dimensional or one-dimensional.
Yes, I mean, like, yeah, you have to set momentum to 0 in that sense. Then yes, what you're saying is correct in that sense. It'll be a dot sort of property. Yeah. And so from here, what we expect is that the poles will occur whenever the gamma function, the numerator, has its parameter either to be a negative integer or 0. And from there, we get that relation at the bottom, which we expect. And so these are two things we expect. And let's compare that with what you get numerically. And so this is the pole structure that you get. Small things to note here is that, yes, the temperature is quite small. D by Jj is the coupling strength is 0.005. I have not mentioned here, but gamma is set to 1 for simplicity. And yeah, so this is what we get. So we see this diffusion sort of thing that appears here. We see these capped modes appear at all of these negative integers starting from -2. So these are the things we expect. So yeah, we have this short-lived diffusion mode. I'll explain short-lived in a little bit. But yeah, for small enough omega and p, we have these. It's not a set; it's just a diffusive pole, and this is where hydrodynamics is. Yes.
This is numerics for those exact equations you had on the previous slide, or this is numerics contains numerics?
This is literally just taking the GR and epsilon, inverting it, and looking for the zeros.
Are all these poles of the type from the gamma function, or are they?
No, they're from the gamma functions that are these ones only.
Yes.
This diffusion one does not come with the gamma functions.
But that has a different origin.
Yeah, so that is exactly was the diffusion that I was talking about before. That is at least the one until that collision is going to be the diffusion section. And then there'll be more complicated things that occur after the collisions, which I'll talk about in a second. And yeah, so we have these this short-lived diffusion pole. We have these gapped modes, which I was talking about, which starts from -2. It starts from -2 because I'll just go back to H. If we set P to 0 and gamma to 1, we see that H is equal to 2. And so we expect the imaginary part of omega by 2 pi t to have poles from -2 and -3, -4, -5. So yeah, this is what we have. The interesting thing is the collisions between them. And this is where hydrodynamics breaks down. And this is because whenever these poles collide, it actually gains a small real part. So if we look at the first collision, which occurs just below 0.4, so we see on the plot over here, you see a very small dot that appears here. And this keeps on increasing as the collisions keep on occurring. So yeah, hydrodynamics does not have these real parts that should appear. That should appear in this omega real part of omega versus p plots, and so that means hydrodynamics is breaking down. We'll see that more fleshed out by seeing a proper non-analytic term appear in our expansion for omega. But we'll do that again a bit later.
Sorry, so these are the closest, if you look in complex P, these are still the closest singularities, this collision.
Complex omega, you mean?
P, you said this is
complex omega.
Yes, but you said this sets the applicability of hydrodynamics.
Yes.
Which would be the closest collision in the complex P plane.
Mm-hmm.
You said this is a real P plot. So I'm just wondering if this is still the closest singularity in complex P. Because you have the analytic expression for all P. So
yes.
I'm just wondering if if you look at complex P or not.
Let me have a look. I don't remember.
Yeah, I guess I'm trying to understand maybe better the motivation for looking at these higher frequency poles. Or, I mean, diffusion we expect to be there.
Yes.
General diffusion is limited to the lowest frequencies and largest wavelengths, and in general it will break down, and the details of that breakdown depend on the details of the system you're looking at.
Yes.
So I guess here you have this because you can solve the model, you see how it's breaking down.
Yes.
But otherwise, is there something useful? Like what is the useful information that's contained in all this kind of high frequency?
Well, I mean, the idea is to sort of compare with what you would get in holography, because in holography this has been done, and which I'll show in a little bit, where you have these very similar plots, and there the idea is also to see where where does hydrodynamics break down, and it is similar sort of in the case for the SYK. It is more fleshed out in the charge case. The charge case for the SYK is a slightly more complicated affair, which is something that I'm looking at the moment. But the energy one is done, and so I'm sort of trying to have a way to see how these things compare in the two different theories. And yeah, this is a sort of proxy for that in a way.
Okay, thanks.
Perhaps I can interject. These are not really high frequencies, right? Because they're all frequencies over the temperature.
I see.
So if you think of couplings, that's not high frequency, right? High frequency would be frequencies of order J, the coupling, or let's say order Fermi energy. So here we are at much lower frequencies than those. So here you could say, well, say you measure AC data, and you see a peak at the frequency over the temperature. Is it a Joule peak, or what is it? And at least in these SYK models, there are all of these excitations at frequencies over the temperature, and they're all controlled by the Schwarzschild fixed points. So they're here for a very precise reason, at least within these models, presumably also within YSYK models, although I don't have calculations for that.
Okay, that makes sense. Thank you.
Thank you. So yes, there is this breaking of hydrodynamics that occurs at these collisions. And another small observation is that initially that these real parts go back to zero after the collision, but after enough collisions, it always has a real part, and these modes, which was initially diffusive, this mode which was initially diffusive, but now which are called capless, this stops interacting with these modes that come from the reparametrization variance, or from the Chauvian action. So these are the main things. And from holography, this was the result I was talking about, where this a similar calculation has been done from holographic theory. Note that this is the minus sign, so it is technically the same plot. There are small differences that occur. For example, the collisions occur in the complex plane for the SYK case, but for the holography case, they occur in the real plane. And so in the imaginary plot, they don't actually fully have a collision sort of per se. If you were looking at the complex plane, you would see them. And this is probably due to a different microscopic origin of the theory. But since they have similar IR theories, this is why the plots look almost exactly the same. And another point is that the radius of convergence is set by the first collision between the diffuser mode and the cap modes. And this occurs at I omega being approximately 4 pi t. This obviously is approximate. The more you reduce temperature, the more exact this becomes. But also that also shows that minus I omega, the radius of convergence goes to zero the moment you set temperature to zero. And this is what we wanted to check. That is really the case. And yes.
I'm confused about the statement. So at very small k, very small omega, all modes are diffusive. So they don't have any real part. So the first collision should happen precisely only on the imaginary axis. So I'm confused about the statement that the collisions happen in complex W or real W.
Repeat your question, sorry.
When you first start at very small k and very small omega, all poles, all of them,
Yes.
that you have only have an imaginary part. They
Yes.
have no real part. So the first collision is going to happen just on the imaginary axis and zero real part. So I'm confused about the statement that the collisions happen at complex W. They happen. The first one happens at strictly imaginary W. Is that correct?
At very small omega and k will be only these ones, right?
Yeah, but they have no real part.
Correct. This
So
has
the
no
first
real-
collision, which as you track k, the
Yes.
first collision will happen strictly imaginary omega, not at complex omega.
But when you say very small omega, very small k, it'll be with respect to temperature, right?
Just your plot.
Yes.
You
So
start-
here it's fine.
Yeah.
But when
Can I make the right permutation of words so that that sentence makes sense?
Okay.
So then this should be note that unlike the SYK case where the pole collisions occur at real P, real wave number, the collisions occur for complex wave number in the holography case. In this plot, the collision is happening for complex K, because here it's an avoided crossing, so you will only see the collision once you would make K imaginary. Whilst in SYK, they occur for real wave number. And that difference is just likely due to the different microscopics in holography and in SYK.
You think it's not this plot which is relevant?
Sorry, what?
So you're saying in holography it's not this plot which is relevant?
This is the holographic plot.
Yes, but you're saying the collision occurs at imaginary k.
Yes.
So it's not, none of these are the relevant collisions. These are all
They're not actual.
These are not actually,
exactly.
these are not collisions
This
for
is
real
just
K.
a-
they're
So
avoided
this
crossings.
plot looks very similar to the plot you showed on the previous slide.
Yeah.
So the one they're colliding and the other they're not.
yes.
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 So they're not.
The difference there is just some numbers that change between holography and SYK.
So yeah, we wanted to look at what happens at zero temperature. And so yeah, so the idea was to look at the Green's function from before, look at the strict temperature to zero limit and see what happens. And we see that from these blue dots, although they say that it looks like it's approximately 0, there is always going to be a real part that appears for omega. And to check this, I sort of try to look at the expansion for omega in terms of p, sort of inspired by how it would work in diffusion, and try to see where we will actually get our first non-analyticity. And we see that it is in the p to the power 8 term at the end, where you have this log p term that appears. And along with it, you have this real part that also appears in p to the power 8 in the term before. Note that there's an I on the left, so there's a plus minus I pi 4, I think, yeah. And so this is the real part that is appearing, which is actually causing this to appear. And so why does it always have a real part? Well, that's because all these gapped modes will coalesce into a branch cut when you set t to 0. Since again, when we we're setting t to 0, we were saying that omega by 2 pi t should be equal to some numbers, some integers. And so when we set it to t to 0, omega equals to 0 will have multiple branch cuts, multiple poles, and that will be coalescing into the branch cut that I was talking about. And since this gapless mode crosses this branch cut, technically this branch cut, it is always going to have a real part. And yeah, so there's a complete breakdown of hydrodynamics at this level. The hope is that trying to compare this with the holographic case is that we are able to see this non-analyticity also in the holographic case, but the calculation is quite difficult in that sense.
There's an I.
Yeah, so there's an I there, and then there's also in front after the plus minus, there's also an I there. That's the real part. Would you like me to see? Maybe you guys zoom it. Can I zoom this? Yeah. Yeah, so there's this I here, which just mentioned, but there's also an I here. This is the real part.
Oh, okay.
Yeah. It's a bit small.
So you say at 0 temperature, there's a propagating mode?
1 second. There is a. Sorry, can you repeat the question?
So
Yes.
yes.
Okay. Thank you.
With p to the 4.
P to the 4.
Sorry, p to the 8.
P to the 8 for energy. Yeah. So conclusions from what's happened. So yeah, we explored the pole structure for the Majorana SYK models. There are many different versions of this sort of models where they are doing some different sort of body interactions, and most of them they have the results which do not change qualitatively, and these corroborate with analysis done in holography. We have these initial gapless modes which interact with these gap modes and sets the radius of convergence of hydrodynamics. And we looked at this interaction as we reduce temperature all the way to t equals to 0. And the next step is to look at, instead of having these Majorana fermions, having charged fermions, and see what happens to the retarded charge density 2-point function. And this is where we hope to have a more stronger connection with holography, because in the holography case, I think it's already shown that it's p to the 4 log p is going to be the first non-analytic term in this hydrodynamic expansion, and trying to see that if it's going to be the same in the SYK case, it's going to be sort of a check in a way with the calculations. And says thank you. Yes.
Can you clarify a little bit what do you mean by the holographic model?
So I think that would know that a bit more well, but yeah, so I think the idea is that they look at an extremal black hole, and then they're looking at the near horizon, like the near horizon geometry, and I think they're putting in fields as far as I remember, and yeah, looking at the so it's ADS 2 cross R2, I think, for an ADS for black hole in this thing, And yeah, they're basically taking that as a setup and using that to calculate quantities that are relevant.
So even without adding charge, I mean, here you looked at energy density correlators. What about number density correlators? I mean, they're, could also maybe have some interesting structure, collective modes, and things like this. Is there? Is that worth looking at?
I'm not sure. I mean, I've not personally looked into it, but it could be interesting. Yeah.
Isn't that what you're looking at these days?
I mean,
Looking at the complex SYK model, complex generalization of that at zero density to look at the charge correlators.
That's what
we're looking at.
Yeah.
Oh, okay.
In that sense, yes. Yeah, yes.
So you had this long formula for the energy correlator.
Yes.
I don't know, I have no concept of how difficult what that was to obtain, but like if you wanted to do a higher dimensional version, so instead of just a line of points, you want to have a lattice of these things. Is that feasible technically?
I think that I think in that sense the generalization is not going to be very difficult, because that would simply be a redefinition in how you define H and how these couplings redefine. I do not think it's going to be too difficult. I think it is, but I don't think the physics changes in a sense. I think you
could get things like shear viscosity for SYK.
Probably, yeah. In that sense, yes, but
conservation here.
Yeah,
that's right. Sorry, yes.
Yeah, the calculations are not too difficult. But
trickier generalizations, and I think when you start having a firm surface.
Right. Any more questions? If not, let's thank Angshuman again.